Dear Crafoord laureates, dear members of the Crafoord family and the Crafoord Foundation, dear colleagues, ladies and gentlemen, as a host for the Royal Academy of Sciences and Lund, which is the city of the Crafoord family, I wish you all very welcome. But I should also start, I think, to tell you it would be good if you turned off your mobile phones, in case you've forgotten that. A very generous donation from Anna-Greta and Holger Crafoord in 1980 to the Royal Academy of Sciences resulted in the first Crafoord Prize in 1982. It is awarded to outstanding scientists in mathematics and astronomy, bioscience, geoscience, and if justified also in the field of polyarthritis. As a Swedish geoscientist, I think it's fair to say that we regard it as the Nobel Prize of Earth Science, and thus awarded every third or fourth year. Altogether, 16 geoscientists have been awarded during 11 different occasions. And for example, at the 25th anniversary of the prize in 2007, we had the big celebration here in Lund when Wally Brucker got the Crafoord Prize. And as you know, the latest Geo laureates are Siko Manabe and Susan Salmon. And we are very pleased to have you here in Lund and look forward to your presentations. But before that, I should tell you something about the schedule. So it starts with Martin Jakobsson from the prize committee, who presents the laureates. And then it's time for Siko Manabe to present his lecture, followed by questions from anyone of you. Then it's time for Susan Salmon with her presentation, followed by questions. Then we have a break around 11 o'clock with some refreshments, followed by a panel discussion half an hour later with Birgitta Svenningsson from Lund, Dorte Dahl Jensen from Copenhagen, and Martin Jakobsson from Stockholm in the panel, together with Susan and Siko. But before that, I should give you some personal perspectives, very short. As a fairly young researcher, I vividly remember my admiration of Professor Manabe's pioneering modeling studies presented at different meetings and congresses in the 1980s and 1990s. They were real eye-openers for a geologist who works with proxy records. I also have strong memories of the discovery of the ozone hole and the processes leading to it discovered by Professor Salmon. During outdoors fieldwork in Antarctica, 1989 and 1993, we had become very aware of the dangers with the ultraviolet radiation. But Susan's discovery and the resulting 1987 Montreal Protocol had started a new ozone trend, making it feel less risky to work outdoor. And that, of course, made fieldwork a bit easier. So thanks, Susan. The protocol also shows that if humans work together, it may result in a better world, although we very lately have heard some alarming news about rising CFCs, especially in the Northern Hemisphere. But perhaps Susan will dwell a bit on that in her talk. So, before I give the word to Martin, I should say that we have a hashtag for social media. We will also have a photographer here for documentation, which The photos might be published and online and also in reports. So if you mind that, please let us know. So, Martin, time for you.
Lite klappa. Thank you, Svante. Dear laureates and dear audience, it's my great pleasure to introduce the two award winners of the Crafoord Prize this year in Geoscience. And I will do that by actually starting to talk a little bit about geoscience. As you realized when Svante gave the introduction, this is every 4th year we will cycle through the different prize categories. And we see this as the equivalence to the Nobel Prize for these different categories. And geoscience is a very, very broad field. My presentation here is geared to a very broad audience to also explain a little bit about our thinking, why we choose the laureates, and also introduce on a very broad scheme their achievements. And then we're going to hear more the details about the different areas. So geoscience, it embraces the atmosphere, the cryosphere, the geosphere, the biosphere, and the hydrosphere. It simply embraces the whole Earth. And this year, we think that the prize goes within climate science. And climate science is the challenge of connecting all the different spheres to understand climate. And this really explains how difficult it is with climate science, because you have to look at the interconnection between the ocean, the cryosphere, the atmosphere, and I didn't have more pictures to actually show up there, but the rest of the spheres. So looking at all the different processes that take place form climate science, and it means that it's very, very broad. And today we are actually presenting the laureates that have done fundamental contributions within climate science. Our 4 fundamental contributions to understanding the role of atmospheric trace gases in Earth climate science. This is what we award this year to Professor Suki Manabe and Professor Susan Solomon. So, for many, it might not be obvious what a trace gas is. It is a gas that makes up less than 1% by volume of dry atmosphere. And the fact is that this very small component Earth's climate is very sensitive to changes in trace gases. And I think that's obvious to everybody if I mention some of the key trace gases that we're going to hear about today. Today we're going to hear about ozone and carbon dioxide specifically, I guess. And these trace gases, they have a fundamental impact on climate, specifically then, of course, carbon dioxide. So you can see on the left, on the right chart there, you see that argon is the biggest components of the trace gases. The other are much smaller components, but yet so important to understand. So if I begin with Professor Suki Manabe, we are awarding Professor Suki Manabe for creating the first global numerical model after groundbreaking studies of atmospheric dynamics in the 1960s. And I should say then that this work is the fundament that we stand on today when we are using climate models numerical climate models in so much research. And it's so important for us to look into the future, where we're going, where climate is going. We wouldn't be able to do that if we didn't have these tools available that Professor Manabe worked on. And he used this climate model to perform 3-dimensional study of the temperature effect from increasing carbon dioxide. And yesterday I actually asked, why did you do this? And the answer I got, I was curious. This was a fun game. I wanted to see how it worked. And I do think that this is the fantastic part of basic research. You actually do something because you're curious and you want to understand how it works. You don't necessarily have the impact, what's going to happen with your results on the other end here. You simply want to understand how Earth works. Today we know how fundamentally important the work was. But I don't think that was obvious when Professor Suki Manabe started this work. Then we have a little explanation what a climate model is. It may not be, we're sure we're going to hear more about that, but it might not be obvious to everybody what a numerical climate model is. And I'm going to try to say that with a big overview. A climate model, a numerical model, you can see it as it is a numerical model that tries to simulate Earth climate. And I like to envision it as if you drape grid cells, you see these grid cells here, around the Earth. And within these grid cells, you solve the equations necessary to look at the processes. And the grid cells will then provide results to each other, and together they simulate the whole Earth climate. So if you're looking, for example, like a component of carbon dioxide, you will put those equations into these grid cells, and you will run the model and you will get the results. That's a very brief layman's explanation of a climate model. And then, of course, it's driven by the sun input. And the more complex you make it, the more it will take in. Professor Susan Solomon, she solved the 1980s enigma, puzzle, riddle. We discussed a lot what to say here. Why the protective ozone layer over Antarctica had become dramatically depleted, with an ozone hole repeatedly forming in springtime. She explained the link between man-made chlorofluorocarbon emissions and the ozone hole of Antarctica. She also showed critical links between ground level ozone concentration and climate, which I'm sure is not obvious to everybody. But we all have heard about the ozone hole. And it was a mystery why it was created a hole over Antarctica every year. And there was fundamental breakthrough to actually resolve this puzzle. And as we heard, that led eventually to banning of chlorofluorocarbons. And I'm as grateful as Svante that we don't need to have protected armor when we're out working today because of the sun rays if we don't have the protecting ozone level. So this is a fundamental research, again, driven by curiosity and trying to understand how things work. So we are going to hear much more about this. This, again, is a very overview introduction. But what is happening is that we have chlorofluorocarbon emissions. They come from spray cans, refrigerators, air conditioners, and many other industrial products. They come in over Antarctica. They're very long-lived. They get into the high level, up into stratospheric clouds where they are bound. And it's very cold in Antarctica, so you have ice crystals. And nothing is really happening with these until you get the sunlight coming in. Then you get photochemical reactions that actually lead to breakdown and depletion of the ozone hole. And that's why we had the repeated ozone hole coming in the spring. You bulk up the chlorofluorocarbons and then reaction takes place in the springtime. And we're going to hear so much more about that, so I'm not going to go into any more details. So with that, I think I'll leave it at that. And now I'm hopefully as intrigued as you are to actually listen more about the details of these great fundamental discoveries, achievements, and contributions to science, which we are, I would say, extremely happy that they did take place. Thank you.
Please.
It is a great pleasure to be selected by Royal Swedish Academy of Sciences to receive the Crafoord Prize, established through the generosity and far-sightedness of Mr. and Mrs. Crafoord. It is likewise a great privilege to give a talk on climate change, on the subject that I have enjoyed studying throughout my career. The atmospheric concentration of carbon dioxide has been increasing, as shown in these figures. and has increased over 30% since the pre-industrial era. Global mean surface temperature has already increased by 1 degree centigrade. It is projected to increase an additional 2 to 3 degrees centigrade by the end of this century. During last several decades, we have studied the mechanism of climate change using numerical model of climate that is based upon laws of physics. On this occasion, I would like to discuss the role of greenhouse gas in global warming. As shown in this figure, heat balance of our planet is maintained between incoming solar radiation, indicated by red arrows over there, and outgoing terrestrial long-wave radiation coming from Earth, as indicated by yellow arrows. And given the outgoing long-wave radiation observed from satellite go around and observe the long-wave radiation coming out from the atmosphere, one can compute planetary emission temperature from the Earth going outward using Stefan Boltzmann's law of black-body radiation. This is thermodynamical terminology, forget me that. And the temperature that's obtained is minus 18 degrees centigrade. That is much lower than the temperature of Earth's surface, which we enjoy, which is plus 15 degrees. The difference between these two is owing to greenhouse effect of the atmosphere. So that greenhouse gas usually considered to be air pollution and so forth. But it's turned out that greenhouse gas is indispensable for our life. Without greenhouse gas, we can't live on this planet, which would be minus 18 degrees centigrade. And existence of greenhouse gas is already established by the satellite observation of outgoing radiations. And the next figure I just created to indicate, this is what I just said here, as you can see, how the effect of the greenhouse gas, which is 33 degrees centigrade. The next figure is constructed in order to illustrate graphically the greenhouse effect of the atmosphere. The slanted line, I should do this. This one. This shows the distribution of temperature in the troposphere, which increase almost linearly with respect to height. And the black dot, which is on, I keep pushing the wrong button, in the middle of troposphere, located in the middle troposphere, indicates the effective emission center of outgoing terrestrial radiation. As pointed out already, its temperature is minus 18 degrees here, and it's colder than the surface temperature by as much as 30 degrees centigrade. This is a greenhouse effect of the atmosphere. Here I would like to explain why the atmosphere has such a large greenhouse effect. The radiative transfer in the atmosphere obeys what we call Kirchhoff's law, which is the law of thermodynamics. Forgive me the little technical. The law requires that at each wavelength, absorptivity of a substance is equal to emissivity, which is defined as a ratio of actual emission to theoretical emission of black body. Because Earth's surface has emissivity that is close to 1, it emits upward flux of long-wave radiation almost as black body. Black body of 255 degrees Kelvin. Sun emits almost black body radiation of 6,000 parts per million, just for your information. As this upward flux penetrates into the atmosphere from outside, penetrating the atmosphere, it is depleted due to the absorption by greenhouse gases in the atmosphere, but it is accreted, the emission from the atmosphere itself, according to Kirchhoff's law. Because temperature of the atmosphere as a whole is colder than temperature of Earth's surface, as you can see in this figure, it is expected that depletion of upward flux is larger than its accretion, reducing substantially upward flux of long-wave radiation emitted by the Earth's surface before it reaches the top of the atmosphere. Thus, atmosphere as a whole reduced by about 40% the upward flux of long-wave radiation emitted by the Earth's surface, helping to maintain warm and habitable planet at the Earth's surface, which we enjoy now. I think it's easiest way to explain this greenhouse effect just act like a blanket for us, you know. And if you have more greenhouse effect, temperature is warmer. That may be the easiest way to explain greenhouse gases, global warming. But I would like to talk a little bit about the mechanism of global warming for the convenience of later explanation, which is the main topics I'm going to get into. So try to explain why global warming occurs. Now, if the concentration of greenhouse, such as carbon dioxide, increases, the absorption of upward flux increases if atmosphere gets more opaque before it reaches the top of the atmosphere. Thus, absorption of upward flux from the lower layer of atmosphere increase more than the absorption of upward flux from the upper layers. If you suppose you have an infrared eye and look down the atmosphere, and you can see lower part of the atmosphere is hard to see because atmosphere is opaque. You can see better upper part of the atmosphere. Suppose you make that atmosphere more opaque, make it much harder to see the lower layer of the atmosphere than the upper layer of the atmosphere. This means the more the opaque the atmosphere, higher the altitude of effective emission layer of the atmosphere. Can you understand that? Yeah. And so the more greenhouse gas you have in the atmosphere, effective center of emission layer go up. And so I just go to next one here. As indicated by the point A, allow go upward. Now, because temperature of troposphere decreases with increasing height, so that effective emission temperature go up higher, that means it's reduced outgoing radiation. The more opaque the atmosphere, higher is the effective center of emission, thereby reducing outgoing radiation from the top of the atmosphere. So in order to restore the heat balance of the atmosphere surface as a whole, you have to warm up the troposphere. You have to warm up the Earth's surface, thereby restoring balance. This is the mechanism of global warming. The change in the concentration of greenhouse gas, this is an important point which I have to use in my talk, is not only decrease the upward flux of long-wave radiation, but also it affects the more the downward flux that reach a ground surface, which has a profound effect in climate change at the Earth's surface. So suppose suppose if the concentration of greenhouse gas increases in the atmosphere, the infrared opacity of the atmosphere increases, as I noted already. Thus, the absorption of downward flux from the higher layer increase more than the flux from lower layer due to the difference in the thickness of underlying layer. Getting confusing? Sorry. Yeah. So that the more atmosphere, more opaque the atmosphere, lower is the emission of the downward flux. Emission of downward flux originates from point B. So you made the atmosphere more opaque. Effective emission center come down, thereby increasing downward flux of long-wave radiation, thereby making the temperature Earth's surface warmer than less opaque atmosphere. So I try to explain this, and I hope I didn't confuse you. And over sufficiently long period of time, Earth's surface sooner or later return to the atmosphere all the downward flux of long-wave radiation coming from above. So, and then with heat energy returned upward in the form of sensible and latent heat flux, dry and moist convection. They bring back into the atmosphere. So that is why temperature just doesn't include just Earth's surface, but return into the troposphere, all the way to the atmosphere. So the more CO2 you have, the warmer the not only Earth's surface, but also entire troposphere warm up. So this is the actual mechanism of warming, of global warming. But the magnitude of warming is such that consistent with the change in upward flux, which I discussed earlier. Maybe I better switch over to. An important factor that affects the magnitude of global warming is the positive feedback effect that involves water vapor. As we know, water vapor is the most powerful greenhouse gas in the atmosphere. And it absorbs and emits over much of spectral range of terrestrial long-wave radiation and is mainly responsible for the powerful greenhouse effect of the atmosphere. In contrast to long-lived greenhouse gas, such as carbon dioxide, with residence time of a few hundred years, water vapor has a short residence time of a few weeks in the troposphere, where it is added through evaporation from the Earth's surface and is removed rapidly through precipitation. Thus, the absolute humidity of air is bounded by saturation, preventing relative humidity from exceeding 100%. As we know, saturation vapor pressure of air increases with increasing temperature, enhancing the moisture holding capacity of air. Thus, absolute humidity of air usually increases with increasing temperature, thereby increasing the greenhouse effect of the atmosphere. It magnifies the greenhouse effect of long-lived greenhouse gas, such as carbon dioxide. It doubles or triples, depending upon what effect you put in there. It was towards the end of the 19th century when Arrhenius, famous Swedish scientist, made the first attempt to estimate magnitude of climate change in response to the change in the concentration of greenhouse gas in the atmosphere. Using one-layer model of atmosphere combined with heat balance model of Earth's surface. He's the first person to use the climate model, in a sense. Yeah. He estimated the change in surface temperature in response to large change in the atmospheric concentration of greenhouse gases. I am impressed very much that he realized already the importance of the water vapor feedback at that time and incorporated it into his computations. His paper was published in 1898. This is several years before the publication of Planck's quantum theory of black body radiation. It is remarkable that Arrhenius conducted these truly pioneering studies. It was in the mid-1960s when Mr. Weatherford and I made an attempt to tackle this problem using one-dimensional vertical column model of the atmosphere, in which heat balance of atmosphere is maintained through close interaction between radiative transfer and convective heat transfer in the atmosphere. Using the model, one-dimensional column model, we computed the vertical temperature profile of atmosphere in radiative-convective equilibrium. The computation was repeated for 3 different concentrations of carbon dioxide. First one is 150 parts per million, then the 600 parts per million. For your information, 300 parts per million was the concentration of carbon dioxide near the beginning of the 20th centuries. It is approaching now 400%, as you know. In this case, this blue line is 150 parts per million radiative equilibrium temperature. Black line is 300 parts per million. And red one is 600 parts per million. if you look at the lower half of the figures, which is the troposphere, you can see temperature increase every doubling from 150 to 300 to 600. Every doubling, it's increased about equal magnitude. It's increased by about 2.3 degrees for each doubling. This is substantially rather than 1.3 degree centigrade that I got in the absence of the water vapor feedback, which I explained to you earlier, indicating the magnitude of greenhouse, the water vapor feedback contribution. It was a big surprise for us at that time to find out that stratosphere is actually, what I'm doing here now. This one. Stratosphere is actually cooling when temperature go from 150 to 300, 300 to 600. And for the economy of time, I'm not explaining this mechanism, which is fun to explain because it's related to ozone and everything. But let me skip these things here. The next one, this one-dimensional model we did in 1960 was a first step towards developing three-dimensional structure of the climate model. And so let me explain one of the highlights of results obtained from climate models. This is, forgive me these terminologies, you just get a general impression of the model. I think you explained much better than I did so already. So why I am doing this? 1, 2, 7. This is the three-dimensional model. They consist of three components. One is the atmospheric general circulation model, which is indicated by green here. And then you have an ocean general circulation model, which is indicated by blue, and heat balance, water balance model of continental surface, which is indicated by brown box. And they are exchange heat, momentum, water vapor through the interface. Using this model, we simulated on the computer three-dimensional structure of the coupled ocean atmosphere system. We then evaluated the response of model climate to gradual increasing atmospheric carbon dioxide. Although initial version of the model was constructed in the late 1960s in collaboration with Kirk-Bryan, it took 2 more decades before the model climate was made realistic enough for a global warming experiment, which I'm going to describe here. Here, I would like to present the results from the experiment that we conducted in the late 1980s, about 30 years ago. In the experiment, the model was forced by gradually increasing atmospheric carbon dioxide at a constant compounded rate of 1% per year. This rate is roughly equivalent to the rate of increase in radiative forcing since the late 1980s, not including ozone change. The upper frame of this figure illustrates the distribution of predicted change in surface air temperature by the 70th year of the global warming experiment, when atmospheric concentration of carbon dioxide doubles, which actually happening toward the latter half of this century. So it may be compared with the bottom frame of figure, which illustrates geographical distribution of observed temperature during last several decades. When multi-decadal rate of global warming, last several decades, when that multiple decadal rate of global warming has been the most pronounced. In order to facilitate comparison between geographic pattern of predicted observed change that are different by a factor of 5, colors are chosen such that value at the color threshold in the upper frame of figure are 5 times as large as those in the lower frame of figures, highlighting the pattern of warming rather than its magnitude. And comparing a pattern of predicted change with that observed change, one notes that surface temperature increase almost everywhere, with land area warm faster than adjacent ocean area in both model and observation. As explained already, the downward flux of long-wave radiation increases as greenhouse gas increases, and that's why it's warm up everywhere. The very simple explanation. And thereby increasing surface temperature. As this figure indicates, the magnitude of warming is larger over continent than ocean. You can see, this place. See, this is North America here. This is Eurasia, and ocean is less. And another thing that happens is that temperature increase about 2 degrees, 3 degrees, 5 degrees. It's increase with increasing latitude. And this is due to the fact that snow cover retreat forward in high latitude, reflect less sunshine. And there are other reasons, but let me skip that. And so that's what is happening here. Why it's what we call polar amplification of global warming. But what is so surprising about is that warming is very small. Look at here, 1 degree contours. Northern hemisphere, very large warming. Its contrast is huge. And 1 minute, that's maybe 3-4 minutes. Yeah. So, but then look at the observed, and this is 60 degrees south. Forward of 60 degrees, you don't have any data, no data over there. So it's not shown here, but already showing that there is practically no warming in southern hemisphere. Why this happens? And I'm not going into detail because already I have only 1 minute, but no warming in southern hemisphere. Actually, there's many reasons for this. But the reason what is happening in this model is actually in the circumpolar ocean in winter, sea ice formed. And when sea ice forms, then they brine rejection. They create a patch of dense cold water which sinks deeply. And then, so that warm anomalies sink very deeply in the ocean, thereby reducing the warming. Thermal inertia of ocean become very large because of large convection, deep convection. And so this is why the warming is in turn resulting in the corresponding increase. So warming is very small over there. Now, the global warming affect not only global mean rate of precipitation and evaporation, but also their geographical distributions of precipitation and evaporation. When temperature increases in the troposphere in response to the increase in the concentration of greenhouse gases, it is expected that horizontal okay, now they should go. Yeah, let me. Global warming involves change in not only in temperature, but also in the rate of evaporation and that of precipitation. If the concentration of greenhouse gas, such as carbon dioxide, water vapor increase, then the downward flux of long-wave radiation increases, as I explained already, illustrate using this left-hand side of features. Thus, it is expected that rate of evaporation also going to increase because more energy available for evaporation. The global scale increase in the rate of evaporation, in turn, result in the corresponding increase in the rate of precipitation, thereby accelerating pace of hydrologic cycle, so that global warming accelerates the hydrologic cycle. Global warming also affects not only global mean rate of precipitation and evaporation, but also their geographical distributions. When temperature increases in the troposphere in response to the increase in the concentration of greenhouse gases, it is expected that the horizontal transport of water vapor by large-scale atmospheric circulation also increase in the troposphere, as the absolute humidity of air increase with increasing temperature. This is the main reason why the distribution of precipitation change differ from that of evaporation due to global warming, affecting substantially the distribution of water availability, such as the rate of river discharge and soil moisture at continental surface. As indicated in our numerical experiment, river discharge is going to increase in many water-rich regions of the world, increasing frequency of flood. On the other hand, soil moisture is going to decrease in many semi-arid regions of the world, increasing frequency of drought, as happening in the southern Europe, southern California, Australia, sub-Saharan region, Sahel, and grassland of Africa. The implied amplification of existing difference in water availability between water-rich and water-poor region could present very challenging issue for the mankind. Thank you. Sorry. time excess.
Questions?
Yeah.
Any questions to Professor Manabe after this very enlightening lecture about the complexities of global warming? I have a question. What do you think is the most complicating process during your experiments?
Actually, what I tried to do was there's many complicated process in the atmosphere. The more you look at, the more complicated, just like human bodies.
Yes.
And I decided whenever I want to make some process complicated, then I said, is this additional complexity is warranted in light of my ignorance? So I made it as simple as possible. Because just like a fractal world, you look at another scale, it's almost as complicated as atmosphere itself.
Yes, yes. Yes, Dorte?
University of Copenhagen. I would like to ask, what do you answer? What do you answer when people in the US say, I don't believe in global warming? What do you tell them?
Yeah, I was asked that question yesterday, but one of the important things is the people just don't want to believe, what they don't want to believe. And also, they don't realize this is not just model result is telling something, but also this climate change is confirmed by a great deal of observation, not only ground observation, but also observation from satellite. They can monitor just about any important variable from above the sky. And so but the people who are skeptical about it is never actually look at these results themselves. And they believe what they want to believe.
Yes, I think that's very true. Birgitta, a short question.
Okay, I hope it's short, or you can give a short answer. I think you were into something very important in the end of your talk when you showed that it's not only a change in global average temperature that's important, and it's also other parameters, and also frequencies of extreme events. Is that something that you would like to comment on, extreme events? Extreme temperatures, extreme precipitation droughts, and so on?
Yeah, these events, I think there is the thing, for example, as I pointed out, frequency of drought is increasing. So many key places, as you know by reading the newspapers and so forth. And I think what is important is one of the things is frequency of big flood occurs in Thailand, Pakistan, Bangladesh. And they really increase tremendously. And so I think we have to carefully monitor these things, look at the past record, and then look at very careful analysis of worldwide precipitation record, and so forth, and keep monitoring into forward, so that keep confirming result of experiment by very careful analysis. And we have a big task at hand too, so that we can really trust these prediction is actually happening.
Thank you very much. Okay, I think we have to go on. And now it's time for Susan Salmon to give her presentation, so please.
Thank you. Well, good morning. It's a tremendous pleasure and an honor to have the chance to speak with you today. I want to thank the Swedish Academy, and I want to thank the Crafoord family. And I want to thank Professor Manabe for being my co-laureate, because I can still remember meeting him when I was a young scientist about 30 years ago, and I would never imagine I could be standing here today together with Professor Manabe. So if you're a young scientist, you should try to meet him during the break, because you never know what might happen to you 30 years later. What I'm going to try to do in this half hour is to talk about the history of ozone science, a little bit of atmospheric physics and chemistry, and tell you how my own work fit into that. I'm going to touch on the issue of whether the agreement on ozone depletion to stop ozone depletion, called the Montreal Protocol, is working. And I won't have time to go into all the details of that, but I will touch on that recent paper that received some news press coverage this past week, saying that there's what you might call a fugitive, an unexpected emission going on. And I'll talk about the issue of how the ozone hole affects the surface climate, at least in Antarctica, if not elsewhere in the southern hemisphere. So, to step back a little bit in the history of this problem, the initial interest in ozone depletion really began in the late 70s, actually mid-70s to early 1980s, when it was predicted that if we kept using chlorofluorocarbons and the halons, which are in fire extinguishers, and they contain bromine, which is even more damaging towards ozone, that we might expect to deplete the ozone layer. And we thought we would see a 5 to 10% change in 100 years. So it was a relatively small effect, it was far in the future. Some people said maybe they didn't believe it. It sounded like another climate change, another environmental change problem that we just heard about. But I want to just emphasize that the thing that was the primary use of chlorofluorocarbon at that time was actually something that some of you may remember, and that was the use of them for literally hairspray, deodorant, paint, oven cleaner, anything that came out of a can. The propellants that drove the material out the can were chlorofluorocarbons. And I'll get back to that in a few minutes. So in 1974, people at the University of California, Irvine, Professor Rowland and Professor Molina, wrote a scientific paper saying, hey, you know, if we keep using these things, they might deplete the ozone layer. So they were the first ones to really call the world's attention to this problem. And that's the basis for those predictions of 5 to 10% in 100 years. And they pointed out that these molecules have very long lifetimes in our atmosphere. We're spraying them all over the place. And they live in the atmosphere for some 50 to 150 years, they said. And when they get to the stratosphere, this is the only place that they can be broken down. They produce chlorine atoms, which go on to react with ozone to make this guy, chlorine monoxide. That guy comes down here, reacts with atomic oxygen, and makes the chlorine atom back again. So that guy can go right back up there and do it again and again and again, over and over. It's a catalytic cycle. You only need a little bit of chlorine to deplete a lot of ozone. And that was the basis of what I'm going to call the gas phase theory of ozone loss. And these two gentlemen shared the Nobel Prize in 1995 in chemistry, together with Paul Crutzen, who was actually my PhD thesis advisor. They were only talking about gas phase molecules, and I just want to point out that also for the students, if you read your papers, you should check them and proofread them very carefully, because you wouldn't want to win the Nobel Prize 20 years later for something that had a typo in the title, but that's what happened. But emphasizing these are gas phase molecules, small effect, far in the future. Then suddenly something really amazing happens. I was very lucky to be a young scientist at the time when the British Antarctic Survey announced the discovery of the ozone hole. They said, hey, ozone is changing in an incredible way in 1985. We're seeing 50% loss of ozone in the springtime, and in a place where no one ever said we would have any special sensitivity, namely the Antarctic. So much bigger than we thought and much sooner than we thought, a real ozone surprise. You're all familiar with the wonderful satellite images that NASA produces every year showing you the Antarctic ozone hole. It's a tremendous graphic image. But the British data was very important because it went back to the 1950s. You can see the ozone go up and down a little bit for the first 20 years, and then boom, it just kind of falls off the map, and that's why they wrote their pioneering paper. That was quickly confirmed by the Japanese station, the American station. And basically, it gives you a graphic image. You don't have to be a statistician to see that there's been a huge change here. These are October monthly average values at each of those stations. Antarctica attracts people. People got interested in this. And so it was a perceptible problem. That's the first of 3 Ps that I'm going to argue are very important in helping people address environmental issues. When an issue is perceptible, we do a particularly good job. So why do we care about this layer of ozone in our stratosphere? Well, you know that ultraviolet light is bad for you. It can give you sunburn, which is unpleasant. But worse than that, if it happens too often, it can give you skin cancer, which is obviously very, very serious. And it can also cause cataracts and eye damage. So those are the sorts of effects that happen to humans. So I'm talking really about ozone in the stratosphere. Ozone at ground level doesn't do those things. People talk about ozone smog. That's a completely separate problem that I'm not going to talk about today. So it's good to have the ozone up in the stratosphere where it can protect us from ultraviolet light. It's bad to have it down here because it's actually gives kids asthma, and it's a real problem in that sense. But the other thing that I think is evident from looking at this is that to people, this is a very personal problem. That's the second of my 3 Ps. It's perceptible and it's personal. We'll get to the 3rd P in a minute. So where I was, at the time, I began thinking about the sorts of chemistry that might explain this special springtime Antarctic sensitivity to this chlorine. And together, particularly with my colleague Rolando Garcia, we wrote a paper that appeared in Nature in 1986, arguing that what could happen is that hydrochloric acid and chlorine nitrate, which don't react with each other in the gas phase, could react on the surfaces of polar stratospheric clouds. You may have seen these occasionally in Sweden. You can see them in the wintertime. They're incredibly beautiful. You'll see them at twilight. They look like little rainbows almost in the sky. And so they change the chemistry in a simple and fundamental way. Now you're talking about surfaces, not just gases. And it's going to be the most effective when it's cold enough to form clouds in the very dry stratosphere. We don't get clouds in the stratosphere over, say, the United States. We get them sometimes in the Arctic, but not as often because the Arctic is warmer. So I'll get back to that in a few minutes, too. So the key ingredients are, we load up the atmosphere with man-made chlorine. The amount of natural chlorine is only about 1/5 of the total that we have today. We've totally overwhelmed it with these industrial chemicals. I talked about the use in spray cans, and I'll talk about some other uses in a few minutes. We have to have extreme cold temperatures so we can get these polar stratospheric clouds, and we need sunlight to drive the photochemistry. And where the sun comes in, so there's another picture of those beautiful clouds. Hydrochloric acid and chlorine nitrate don't react with ozone. They're reservoir species, we like to call them. They're stable species until they get together on the surfaces of those clouds. They make this guy, molecular chlorine, which is quite unstable. It just needs a little bit of light to break down. Now you got 2 of these chlorine atoms, and they can go on to deplete ozone catalytically, and I'm not going to show you the details of that chemistry. But the key thing is that the polar stratospheric clouds are what activates the chlorine in a very special way in the Antarctic. So what does that do? Well, that gas phase chemistry that was talked about initially has some potential to affect the ozone layer, as we know. This is what a typical ozone layer looks like. So you don't have much ozone in the troposphere. You have a lot of it in the stratosphere. As you go up, you have even less. So the gas phase chemistry destroys ozone up here. It can't give you a big change in the total integrated amount between you and the sun because it can only attack the high altitudes, which is not where most of the ozone actually is. by having the polar stratospheric clouds there, you can actually hit the heart of the layer. You can take a normal ozone layer that looks like this and turn it into something that I've drawn in a cartoon form like that. So you've got to have cold temperatures, you've got to have sunlight, and you've got to have man-made chlorine. Well, the other great good fortune that I had was to be the leader of the National Ozone Expedition in 1986. So there I am on the tarmac, getting ready to get on a military airplane to go to the Antarctic to make some measurements, which I'll show you in just a moment. And 9 hours later, there we are arriving in Antarctica. It's about noontime. It's about -40 Fahrenheit, which is the same -40 Celsius. That's the one temperature at which they actually are the same. So it's a good number to know. I thought it was the most beautiful place that I had ever seen. As you can see, even though it's noon, it's not very bright yet because it's August. So August is like February. You know how dark February is here in Sweden. It's quite dark, even darker, because I'm at a higher latitude than you down there. One of the things that we did on the National Ozone Expedition, Dave Hoffman and his colleagues launched ozone balloons, and they had an electrochemical instrument on the end of that payload, and the balloon would rise up into the stratosphere, and as it went, we could measure that ozone layer. So here's an example of what an ozone layer typically looks like in, say, August. This is actually from South Pole, but we had similar data from McMurdo in '86. You can see that by mid-September, when now sunlight has returned, like mid-March here, you begin to see a very amazing sort of bites being taken out of the ozone layer. By the time you get to the end of September, even more, and nowadays, by the time you get to early October, basically it's all gone. So you've completely wiped it out at the altitudes, exactly the same heights that we expect it to be, because we know that's where the polar stratospheric clouds reside. So we have these wonderful signatures that tell us that, that this chemistry is right. I mean, it's got the right seasonal behavior, it's got the right altitudinal behavior, the loss is occurring right where the clouds reside, and we have ways that we can measure the chlorine. That was probably the most important thing that my own group did, and that's my colleague Ryan Sanders, who was very instrumental in this work. What we did was to look for spectral fingerprints of chlorine dioxide, a key chlorine molecule closely related to chlorine monoxide. We used moonlight and sunlight at McMurdo Station. And we had to sometimes get up on the roof, as Ryan is doing here, to adjust mirrors, and it was windy, it was cold, and it was an incredible experience for any young scientist. So we would take that moonlight and direct it down into our spectrograph, and we did something very much like a prism. So the white light from the moon comes in, goes through the prism and turns into different colors of light, and we can measure the absorption of that moonlight at particular wavelengths, particular colors of light. So this is what chlorine dioxide looks like. The dotted line is a laboratory spectrum, and the solid line is what we were able to see in Antarctica. So clearly, there was a significant amount of it, 100 times more than there should have been, and 100 times more than you see anyplace else. So it was I think it's fair to say it was the first marker showing us that the chlorine in Antarctica really was totally out of whack compared to other latitudes. Another very important activity were the airborne missions in 1987, a year later, by NASA, NOAA, and NSF, and that included an independent method to measure chlorine monoxide by a laser technique on board that plane by Anderson and colleagues from Harvard. So I wish I had time to show you all of those wonderful chemical measurements. The only thing I'm going to say is that because we had so many independent types of data, they all showed that this chlorine chemistry was extremely perturbed. We also had measurements of hydrochloric acid. We could see that the hydrochloric acid had been just destroyed. So this grew at the expense of that. We also measured the nitrogen compounds, and they all told the same story, that this chemistry was what was depleting the ozone layer, and that's me again. By now, the sun has come back, obviously, and in fact, it's not setting anymore. I think that was late October. So if we compare quickly the Arctic and the Antarctic, I've already shown you pictures that look like this, but now this is comparing historical data from the South Pole, 60s and 70s. October averages used to have a normal ozone layer, and now look what's happened to it in the most extreme cases and in the average. If you compare that to the most extreme sorts of cases that we see here in the northern hemisphere in the Arctic, definitely it looks somewhat similar. You know, we're seeing some of the same phenomena happening in March in the Arctic that we see in October in the Antarctic. We're definitely seeing bite outs, but it doesn't take it down to zero the way it does in the Antarctic. So that's simply because the Arctic is warmer. We have significant ozone loss here, and I know that people are justifiably concerned when the Arctic ozone losses roll over Sweden, which they will do from time to time, but it's not as much as what we see in the Antarctic. I just want to emphasize that I've said a lot about American research in the Antarctic. I think it's clear that the Europeans have been the leaders in understanding Arctic ozone. I don't have time to talk about that in detail, but this is just a picture of the station in Kiruna, and a picture of a balloon launch there, and several campaigns to understand Arctic ozone losses and really figure out why there's so much less ozone loss in the Arctic have been conducted by European scientists involving many people from different countries. So, concern about this led the nations of the world to agree to the Montreal Protocol. First, they said, well, we'll just freeze these emissions. We'll not let you make any more than you made the previous year. And that was not that difficult to do in the sense that there were only ever about 20 different companies that were making the stuff worldwide, and they freeze the production, I should say. The important point, emission is not the same as production, and I'll touch on that in a second. So let's just not make more next year than we made this year, and if you kept doing that forever, chlorofluorocarbons would have still increased dramatically because of the very long residence times, the long lifetimes of these gases. But that's not where it stopped. Once the Antarctic ozone hole was understood and accepted by the scientific community, which took a few years, the diplomats met again in London in 1990 and agreed to phase them out entirely in developed countries. And then they met over and over again till Beijing in 1999, when they agreed to phase them out in developing countries as well. So we're following very close to the zero emission line now, and that has had an enormous effect. Let me show you just a little bit more about how it all happened. It wasn't just the diplomats at all. So if you take a look at something else now, these are the metric tons of chlorofluorocarbon sold, total chlorofluorocarbon, as a function of year. In the United States, the rest of the world, and then the total, you see something very interesting, which is sometime around 1974 or so, the American sales start dropping. The rest of the world kind of flattens, but never actually drops. That dropping wasn't due to the Montreal Protocol. That wasn't signed until 1987. It wasn't due to the discovery of the ozone hole, which didn't happen until 1985. It happened because that theory paper that won the Nobel Prize was published by Molina and Rowland. And what that did was to make people concerned, even though it was only a theory and far in the future. Many people turned away from their spray cans. So, you know, all they had to do was that, which is not that hard. So lots of people can do things that involve environmental change when it doesn't inconvenience them too much, because people do care, actually. And if there are simple things that people can do, they will find them. That made good business into bad business for the US chemical companies, and as a result, they were pretty eager to get out of the business. In most of Europe, that didn't happen. I'll name an exception in a minute. And that's why, in fact, in Europe, people continued to use chlorofluorocarbons in spray cans well into the late 1980s and early 90s, so much later. So really, I would have to say that consumer pressure in a case like this was very important. And I really feel uplifted when I think about the role that people played in this. And since I'm here, I can't help but mention that actually Sweden was the first country in the world to announce that they were going to ban spray cans entirely. And you did that about 10 months before we did, actually, in the US. So you were the leaders of the entire world in banning spray cans, but not the rest of Europe actually didn't follow suit. A few countries did. Norway did, but not everyone. So spray cans are not the only use, and I should emphasize that it's okay to use spray cans now. They don't contain chlorofluorocarbon anymore. Other things get the material out the nozzle now. But they were used in other things that were also phased out, thing after thing after thing. Styrofoam was another major use of chlorofluorocarbons. It made the little bubbles in the foam. But nowadays, you get your Big Mac in a cardboard box instead of a styrofoam box, and that's why. They were also used as solvents, and nowadays, in many of those applications, you can even use lemon juice. So it's really been amazing. What did this do for the world? Well, it avoided the whole world looking like this by 2060. So basically, the whole world would have been under an ozone hole by 2060. You would have had many, many millions more skin cancer cases worldwide. We really did save the planet. One of the issues is the replacement in refrigeration is something like this molecule, which is an HFC. It has fluorine and hydrogen, but no chlorine. So it doesn't deplete the ozone layer. Fluorine does not deplete the ozone layer. Chlorine and bromine do. But it is a greenhouse gas, and it's important for climate change. So it is also now being phased out under the Montreal Protocol. The Montreal Protocol did not have protection of climate as its primary goal. It's to protect the ozone layer. And yet, it actually did more to protect climate than, say, the Kyoto Protocol. Actually, about 5 to 10 times more, depending on how you count it. And it's about to do more again by phasing out the HFCs, assuming that that continues to move forward. That will actually shave about somewhere between 0.2 and 0.4 degrees Celsius off of 21st century warming. So it's not zero. So is the protocol working? I think it's fair to say that it is working. If we look at the amount of chlorofluorocarbon, 11 in the atmosphere, we have stations all around the world, so we can divide it up into zones if we want to. You can see the northern hemisphere gets ahead of the southern hemisphere because more people live here and we've emitted more of it here. This is when the emissions began to turn around 1990 after the London meeting, as I told you. And this is what chlorofluorocarbon 11 is doing now. But if emissions were zero, the northern hemisphere and the southern hemisphere would merge. And they're not quite merging. That's been a conundrum, actually, for scientists. We expected them to merge by now, or get very close to it. And recently, last week, a paper was published in Nature announcing that there's good evidence, not only from this difference between the hemispheres, but also from direct measurements on the ground, that there's an additional small source coming out of Asia. We don't know which country. We don't know for what reason. It may just be an accidental byproduct of making something else, like a plastic. It might be that someone is still making a little bit, but it's not huge. As you can see, this is where we expect it to be by now, is line number 1, and this is where we actually are. So we've still dropped tremendously. And if you look at the other chlorofluorocarbons, this is only one of about a dozen molecules that are important. They've pretty much behaved almost as we expected. So in the last few minutes, I just want to talk a little bit about the influence on climate. Ozone loss is not a cause of global warming. Professor Manabe just gave you a beautiful explanation of how carbon dioxide drives climate change. It is the primary cause of climate change. So ozone loss is not what causes global warming. The ultraviolet light that ozone absorbs actually gives you skin cancer, but it doesn't heat the planet's surface. Visible light is what heats the planet's surface. But one thing that absorbing that ultraviolet light does is actually to heat the stratosphere quite significantly. It's the major source of heat to the stratosphere. So when we completely destroy the ozone, as we have in the Antarctic, the stratosphere gets much colder. And you're probably familiar with the concept of a polar vortex. You can have a cold, tight vortex, in which case Sweden stays relatively warm because all the cold air is bottled up over the Arctic. Or you can have a wavy vortex, in which case you can get quite cold with a push of Arctic air over you. And of course, it can also come down over us in North America too, depending on how the waves look. Well, the Antarctic vortex in the stratosphere has gotten much colder because there's no ozone in it now at certain times of the year. And what that in turn has done is to actually lead to a shift in where the jet stream sits, and it's made the winds stronger. So you can see how the winds here have strengthened. What that's actually done is to make it, so that's just the trend in the strength of the vortex, if you will. It's made the Antarctic plateau region colder than it would have been since about 1979 or so. And the peninsula region has gotten very hot. So the Antarctic Peninsula is one of the places with the strongest global warming of any place anywhere. Some of that is certainly carbon dioxide, as Professor Manabe talked about, but it's also due to the change in the structure of the vortex and the structure of this wind system. So the ozone hole has really rocked the climate of the southern hemisphere. That wind change, this position of the jet stream has also affected rainfall, extremes. It's had a big effect everywhere, but particularly the peninsula. You can see it's actually made South America a little warmer too. So there's more, in short, there's more warm maritime ocean air hitting this region and less of this cold polar air from the continent hitting that region. And it's also made it windier. That in turn has an effect on ice, and I just in the last minute want to say something about ice. The Antarctic has what are called ice shelves, and you can actually, they do kind of look like a shelf. This is the edge of the Larsen B ice shelf from a photograph taken in 2008. That's just a tongue of ice that's extending way out over the water. As those ice shelves melt, they do not contribute to sea level rise because they're already sitting on the ocean, but they do destabilize the ice behind them. And so you can imagine that as you lose that buttressing ice shelf, the flow of ice into the water can increase, and that's happening quite noticeably on the peninsula and in other parts of that part of Antarctica. And I would argue there's clearly a contribution to that from this change driven by ozone, which has, I think, contributed particularly, and I need to actually get my cursor in there, which is always difficult. I'm going to have to exit the show so I can do this. Come on. Yes, I took that picture. It was really fun. Here we go. So what you can see there is the breakup of an entire ice shelf. I hope it's clear, even though it's small. In a period of about a month, the Larsen B ice shelf just completely disintegrated. That happened in February and March of 2002, and it was certainly driven in part by the warming of that region that is happening because of the ozone loss. And that, in turn, will lead to more flow of ice into the ocean from all these surrounding glaciers. And actually, the loss of glaciers in the Antarctic is a significant cause of sea level rise. So I apologize I couldn't get that going without doing that. But let me just, in the last minute, say a few words that may help us to kind of think about at least my view of the contrast between the two issues. So if you look at ozone depletion, I've already emphasized my 3 Ps. It's perceptible because of these fingerprints that we have scientifically. They can be understood by I've even given simpler versions of this talk to high school students, and they get it. Personal health impacts always make people more concerned about environmental issues, and we know we have practical solutions. I mean, particularly for spray cans, people could make a change without the need for policies. But we also did have some great policy, and some fantastic diplomats helped to pave the way, as well as engineering and innovation to really find even more practical solutions. When we come to climate science, the puzzle is a lot more difficult. We do have a great physical understanding, as was described. We're seeing more and more fingerprints emerging, things like the Arctic warming faster than lower latitudes, for example. And they're becoming more and more perceptible in many places. Not everywhere, but in some parts of the world, it's becoming pretty obvious that summers are getting hotter than they've ever been before, and certainly extreme heat is a serious problem. There's no universal personal health impact on everyone right now, and it's actually the poorest people of the world, the developing countries that don't have the capacity to adapt, that are the most vulnerable. So climate change challenges us to think beyond ourselves, actually, at least for us in the developed world. To consider issues of what's fair globally is absolutely essential, I think, if you're going to deal with climate change. That's a challenge for people, but it's one we have to rise to. Policies have been, I think, very thoughtful, and I don't think You can argue that the solutions aren't practical. They have become practical. So it's amazing how quickly electric vehicles have come on. It's incredible how fast renewable energy is becoming available and cheaper all the time. So really one of the big policy questions is to spur innovation and technology so that alternative energy becomes cheaper and faster and better all the time. So I remain optimistic on climate change. It is a very challenging problem also just because of the embeddedness of energy into the global economy. Very, very different kind of problem than the way the chlorofluorocarbons were. But the story of the Montreal Protocol demonstrates that global policies can be put in place, that people can agree and they can work. So it's just to summarize the things that I've said and to thank you very much for listening. Thank you.
Thank you very much, Susan, for a brilliant talk and the optimistic end. I think we need that. Questions to Susan? Yeah. Lars-Olof?
Wait for the mic. Here it comes.
Paper by Monskat last week that you referred to, CFC 11, I think. Do you have any idea? I think it's not due to new production, it's something leaking somewhere, right?
We don't know. It's possible that it is coming out of old refrigerators. Some of it, certainly, we can say, is coming from old refrigerators, old air conditioners. Here in Sweden, and actually also in Japan, people do a great job of recycling the chlorofluorocarbon out of those systems when they get rid of them. But in other parts of the world, including actually my country, we don't do as well. So there's always leakage from what we call the banks, which is what Olaf, I believe, is referring to. And I think that's contributing. I'm actually trying to do an analysis of that within my group right now. I'm excited about doing that. But the evidence that other people have looked at suggests that there's a particular source somewhere in Asia. We don't know what country. So there could be some production. And as I said, it isn't necessarily chlorofluorocarbon 11 that they're trying to make. I think if it is happening, I don't think it's because someone's cheating on the protocol. I think my best guess is it could be an accidental emission because chlorofluorocarbons are used as feedstocks in making certain kinds of plastic. And it might be that the containment in those factories is just not good enough, and so they have a leakage that they aren't doing on purpose, but need to do more work to contain. That's a possibility, or someone could be cheating. That would shock me. China and India have closed down the plants that they had, and we know that the main plants that they had, they have been closed. There's no question. Those aren't operating. So it's either it's not something you can make in the garage. So I just don't think that it's likely to be deliberate. But I think it's going to be a fascinating thing to research. Yes.
Birgitta?
I've always been amazed by the process in these years, 85 to 87, sort of, and how fast everything happened. And I would like to hear your comments, if it really was that fast as we from outside see it, or if you have been thinking about stratospheric clouds before 85, and as a follow-up on that, do you think the Antarctic ozone hole saved us in a way to make the Montreal Protocol happen?
Yeah, that's a great question. Let me answer the last part first. I think if we hadn't had the Antarctic ozone hole, we probably wouldn't have phased everything out as quickly as we have. And that would have meant more chlorine building up every year, and more ozone depletion at mid-latitudes going on. Now, it is also true, though, that by 1988 or 89, We knew that there was already ozone loss at mid-latitudes in places like Europe and North America from ground-based measurements. It wasn't as dramatic as Antarctica. It wasn't 50%, but it was 5 to 10%. One of the best places to see that actually is the Swiss record from Arosa, which goes back 100 years almost. That's just an amazing record. And you can see stable, 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 and then, you know. So it's not huge, 5 to 10%, but it's measurable. So even at mid-latitudes, we were seeing bigger changes earlier than we expected. I think those would have driven action too, but they would have become much worse if it would have taken more time. I think the world was shocked into quick action by the discovery of the ozone hole, which saved us from having an even worse problem, absolutely. The other part of your question was how quickly the evidence came together. I did not personally think about polar stratospheric cloud chemistry until the ozone hole was discovered. But people have known for hundreds of years that polar stratospheric clouds exist. There's fantastic books about observations of them, mainly in Scandinavia, actually, going back centuries. And there were satellite measurements already. And people, even the early explorers, Robert Falcon Scott saw polar stratospheric clouds. If you read his diary, you can see sentences that he wrote about it where he clearly was seeing polar stratospheric clouds. So the link that I was fortunate enough to think about was, hey, you know, maybe hydrochloric acid and chlorine nitrate might react on those things. I had a little bit of a tip-off, I have to be fair. A few years earlier, some laboratory chemists had thought that they saw a reaction between those two molecules happening in the gas phase at a very slow rate. It would be a very unlikely reaction. It's a four-center reaction, which I'm not going to talk about, but you know, you can see, I think, the picture. So that caused a little bit of a stir in the scientific community at the time. If that reaction was going in the gas phase, it would have huge consequences. But quickly they realized, oh, no, it's not actually happening. It's just an artifact because it's on the surface in our reaction vessel. We put the hydrochloric acid and the chlorine nitrate in a tube, and hey, we think we see something, but don't worry, it's only on the surface. Well, after the Antarctic ozone hole was discovered, I began thinking about this, and I said, oh, surfaces, well, what about clouds? Now, it's been a long time coming to have a complete understanding of the physics and chemistry of those clouds. Another thing that we got lucky with is that, you know, we thought initially that they were water ice. They turn out to more often be made of liquids, sulfuric acid, water, and nitric acid, and also nitric acid trihydrate ices. So the composition of those clouds is more complicated than we thought. But it doesn't matter what they're made of for reasons that are a little complicated, except I can say when it gets cold enough, any kind of surface gets reactive. So a lot of that has to do with water depositing on the surface and giving you what's sometimes called a quasi-liquid layer in the physical chemistry community. And that allows processes on ice surfaces that are a little bit wetted to be very similar to a liquid. So we got perhaps lucky on that in a sense. Otherwise, we would have really had to work hard to understand the microphysics of those clouds, what they were made of, and that would have taken longer. But the other thing that we had great good fortune was to just have these kind of instruments. The instrument that I worked with at Visible Spectrograph had been developed about 10 years earlier. And the main reason was because of concern about supersonic transport. It was designed to measure nitrogen dioxide. So the fact that people were starting already to think about stratospheric chemistry and what chemicals could be measured is why all this instrumentation was all in place already. You know, we had all the instruments. Some of them had been flown on balloons, but we didn't know what was going on in Antarctica because we didn't have satellites then. So the only way to we had satellites just for ozone. We had no satellite measurements of any of the chemicals. Today we have satellite measurements of chlorine monoxide and hydrochloric acid. I mean, if it was happening now, we would know everything. But at the time, the only way to really find out was to go to Antarctica, measure it on the ground, just take the instruments down there, which is what we were fortunate enough to do. And I was very lucky to be a young scientist in exactly the right place at the right time. And I'm very lucky to be with you today. Maybe we should have a break.
Well, I have a short question to you. Do we know if the fauna of Antarctica were kind of impacted?
Yeah, there may be people here who know more about this than I, and I'd be welcoming any contributions on that. It's been discussed a lot whether phytoplankton could be sensitive to the enhanced ultraviolet. I think the evidence suggests that that may not be such a big problem because they can go deeper in the water column and escape the UV. One thing, though, that I am becoming very concerned about personally is krill. So krill are the base of the Antarctic food chain. They, feed the penguins, they feed the fish, which feeds the whales and the seals and everything else that lives in a very, very rich, biodiverse ocean. But the krill spend the winter on the bottom side of the sea ice. So they're larvae, and then they come up and they feed on the algae and stuff on the bottom side of the sea ice. And sea ice in that part of Antarctica that I showed you where the ice shelf has fallen apart is also disappearing. Other parts of Antarctica, the sea ice is actually growing, but that is exactly the region where the krill are the most abundant, is where that ice is going away, partly because of ozone, I would argue. So I'm going to be very intrigued to see how that plays out. We know that the krill population in that part of the Antarctic has decreased dramatically. We know that some kinds of penguins have seen decreases in population there. So it's a matter of some serious concern. I think, biology is quite complicated. It's much harder than chemistry. It's why I become a chemist instead of a biologist. So I think it'll take many years to sort that out. But whatever is causing that decline in Antarctic sea ice, if it's global warming or ozone depletion, and I actually believe it's a bit of both, the implications for the planet are enormous.
Yes.
We'll see.
But we are still optimistic.
Well, we have to change our ways, right? I mean, when we say things like Professor Manabe said, and I said myself yesterday, it was reminded to me that I sounded too pessimistic when I said, well, we think we're going to see 2 to 5 degrees Celsius of global warming in the coming century. Well, that's only if we don't change our ways. And of course, if we change our ways, we could keep it to 2. To get below 2, we probably have to get very creative with ways to sequester the carbon, but people are thinking about that too. So the practical needs to move along, and policies can spur innovation on that. People don't have a simple thing that they can do that gives you a big reduction in emission. There's lots of things that we all, I would argue, can do and should do to be wise users of this planet. It's great how many bicycles we have here in Sweden. That certainly helps to avoid unnecessary carbon emission, but it's not going to give you the kind of reductions that we need. We really need to change the energy system, and so the most important thing a citizen can do is be engaged and demand that the policy people actually do the kinds of things that will allow that to happen. If we could just throw away our hairspray, we would. This is a little different. Okay.
Thank you very much. You can take that at the panel discussion later on. Yeah. So we have 25, 30 minutes break for refreshments, and then we'll have a panel discussion afterwards. Thank you very much.
Ja.
Absolut.
Så, ta. Ja. Ja, visst. Ja. Får jag låna din sån... Själva... Den. Ja, visst. Hej. Ja, visst. Hej. Hör du mig?
Nu har jag alltså inte hörselslingan i mina öron.
Nej.
Då hör jag dig.
Och om du byter till hörslingeläge? Hej. Hej. Ta.
Jag hör sämre.
Ta.
Jag hör hörselslingan.
Ta. Ingenting. Konstigt. Ta. För att när jag kopplar in hörlurar in i denne. Så hör jag direkt in från denna till mina hörlurar. Ta. Hur... Ja, nej. Det ser ut som det ska funka nu. Är du säker på att du har rätt läge på då?
Ja.
För nu ska det... Ja, det är svårt att bedöma, ja. Ta. Ja. För den här bankar bara. Ja. Hej. Ja. Då ska vi nu göra så att vi ska dra upp... Vi behöver lite mer gas. Ja. Hej. Ja. 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 Hej. Ja. Vad bra. Bra att du sa till. Tack så mycket. Ja, vi ska mycket. Ja, men vi gör det. Ja, men vad bra. Jag behöver bara hjälpa hörslingan. Ja, men jag bara kollar. Ja.
Hörde du det också? Nej. Han Stakes hittar inte orden och framför papperna och sådär. Så han också undrar om vi kunde liksom klippa bort det i öppna-versionen. För det kan vi göra. Ja. Och sen på en så började han prata och sen bytte han bilden. Jag såg det ju i filmen, det är rätt tydligt att han gör det för att han är så om vi kunde liksom korrigera det. Jag sa att det kan vi göra liksom. Han är så väldigt artig. Ja. Om vi ska göra en efterredigering av.
Ja, precis. Det känns som att
han pratade ju om att det skulle klippas isär och det skulle ha vignetten då istället och så.
Jag vet inte vad det var med det offerten någonstans.
Men visst, men han sa ju det innan när vi pratade om vignetten, att det klipper isär.
Jag vet.
Så det är klart att det är en extra kostnad. Det är bara att om vi gör det, då kan vi ta höjd för japanens stakning liksom. Forskare vinner priser och sådär och ja, tappar orden. Ta den här pausen och sen är det liksom duration 200% istället. Alltså skitlänge och bara delar liksom. Attending IBC, nej. Staying Hydrologic, nej. Nej. Jag tycker det är skitbra det här med GDPR. Att det är så himla många som bara, ska du inte fortsätta på våra mejl så måste du anmäla det här bara. Nej, det är nu I finally get out liksom. Vill du spela dem med här eller hur var det? Inte repa?
Ja, det är repa.
Vad är klockan? Oj, de sätter sig. Ja, den är 35.
Ja.
Jag vill ta en djupklok.
Det känns som att de är på väg igång. Jag går över i elbilden.
Okay. I think we should start the panel discussion now. And we think that it's nice if you 5 here, Birgitta Svenningsson from Lund, Dorte Dahl Jensen from Copenhagen, Martin Jakobsson from Stockholm, and the 2 laureates kind of start a little discussion, and then it's open for everyone. But before that, Dorte would like to say something.
Yeah, well, first I'd like to introduce myself. My name is Dorte Dahl Jensen. I drill ice cores and work with paleoclimate at the University of Copenhagen. But Susan, I was also quite lucky that I was present in 2007 at the University of Colorado and actually cheered with you and celebrated that you received the Nobel Prize in connection with the IPCC report in 2007. So actually we're looking at a laureate here that's as a woman has received a Nobel Prize and Crafoord Prize 2 times. And it's only done 1 time before by Marie Curie, who received it in 1903 and 1911. So I really want to congratulate you for that.
Well, you're being incredibly kind, and I so appreciate it. I must say, though, that the award to the IPCC was to the organization, and if anyone deserves credit for that, it's Bert Bolin from Stockholm. You know, the individuals who worked on it have to be a little modest and say, well, we were part of a big team, and it's really the organization that was honored, and that owes everything to Professor Bolin. So thank you, but
then I'll answer back. You were actually the co-chair of Working Group 1 of the physical system, so you really did a big job too. Thank you. Yeah.
So please, start discussing. Martin is always good.
Well, I enjoyed tremendously to sit and look at the presentations, and I already picked up and I learned so much. And I think one of the, for me who work with the ice, the big ice sheets and the ice shelves and the coupling to climate, I enjoyed tremendously to actually learn and think more about the ozone relationship to that. At the same time as thinking what Professor Manabe lifted up about production of brine and brine rejection in these areas. And for me, that just highlights the importance of learning more about the system. Mm-hmm. So I think that was, for me, I took notes on my cell phone, and I definitely going to dig in more to that.
Well, thank you.
And I don't know if we have direct comments on this, on the coupling in Antarctica with ozone, projection of brine rejection and as a cooling mechanism, etc., and the ozone as rearranging the system so we get the warming in the peninsula, because it fits very well actually into to what we see. We definitely see a huge difference between East Antarctica and West Antarctica.
Yeah, I guess I would ask Professor Manabe if he thinks that the current model calculations can capture what's going on with the distribution of sea ice in the Antarctic. You know, you talked about brine rejection and the role of that. Does that help us to understand why East Antarctica is different from West Antarctica? Mm-hmm. You think that's part of it?
Yeah. The very interesting issue is raised here. That is, right now, I think more and more observation are very look like certain that there is a huge interhemispheric asymmetry is growing. And what seems to be happening is that although there is some place where sea ice is actually melting rapidly in the near Panama Peninsula, but majority of Antarctic Ocean, sea ice is actually increasing year after year, although there's a huge fluctuation, year-to-year fluctuations. And what is very interesting, also, if you look at the water temperature is not warming up at all. And I have done in this experiment that in my experiment, I increase carbon dioxide with time, but I didn't change ozone. I fixed it in my model, so that ozone effect is not included at all. But what happened is my models actually found out that in the Antarctic Ocean, sea ice actually increasing. And what happened is in the circumpolar ocean, every winter, it's awfully cold. And all the sea ice freezes down to almost someplace 50 degrees south. And this sea ice has been increasing. And then what I dig in, look at them, and then I found out that the water temperature, there is a slight warming penetrate very, very deeply in there. So that what happened is the heat is spread very deeply into the ocean there. And then thereby increasing thermal inertia of ocean, and the sea surface temperature doesn't warm up at all. And why usually if sea ice forms in winter and keep doing this brine injection and dense water keep accumulating, then very quickly convection stops. So that the oceanographer don't believe my result, because also ocean is slightly stably stratified. And, but what happens is the circumpolar ocean, there is ocean is zonally connected through Drake Passage and intense westerly going blow there, and ocean current just going around, and this westerly induce overturning circulations, which is sometimes called Deacon cell. And there is an upwelling over there. And so what happens is sea ice keep producing, freezing, keep producing dense saline deep water, but this upwelling, wind-induced upwelling, keep bringing water upward, and therefore prevent further accumulation of dense water, deep water, and keep running this deep convections. And so this is what is happening. And there is a big debate about this, because oceanographers don't, many of them don't really believe what I got. And so, anyway, that is a sort of brief explanation, though may not be too brief, but my explanation of my result. And, but what is fascinating is Susan's model, you can explain now, but don't have any of these effects. But it is fascinating that there is this stratospheric ozone mechanism which she can explain, and then say, no warming over there, right? You can explain now.
Well,
yeah.
I guess I would have given as a short statement about sea ice that I think West Antarctica is different from East Antarctica. And the reason for that has more to do with ozone loss than it does with carbon dioxide.
Oh, is that right?
It doesn't mean that it's everywhere, just West Antarctica. I'm really only emphasizing the peninsula.
I see.
So it explains very well the observations we have with all the loss around West Antarctica.
But it doesn't explain sea ice expansion in East Antarctica.
No,
Professor Manabe's rightly interested also in sea ice in East Antarctica, which I don't know the answer, but I think he does.
Dorte?
Well, if you look back in time from kind of a paleo point of view, we have this interesting phenomena that when we go into the glacial time, we had 33 events where we had really, really abrupt warmings in the north, abrupt warmings of 10 to 16 degrees just happening in less than 50 years. And by looking at ice cores in Antarctica too, we see that there is kind of a seesaw between the north and the south. When it's warming in the north, it's cooling in the south. So while we see the sea ice is declining in the north, right now, to some degree, we see the sea ice is expanding in the south, which is kind of the same pattern in my understanding too. But listening to your talks, I got to think about that, you know, the very, very fundamental thing is the energy we receive from the sun. And the energy, we receive energy and we radiate energy from Earth. And it gives some different kind of temperatures, balances on the surface. But we can have many balances. And through time, we've had many different surface temperatures, basically receiving the same energy from the sun. So temperature is not a super fundamental physical property. It is the energy exchange that is. And I think that the seesaw with the changing energy between north and south, that we can have up to 16 degrees different temperature in the north just because the energy moves from south to north is extremely interesting.
So I have a question for you, actually, Dorte. I mean, there's so much interest now in whether, and actually also you, Martin, whether the Antarctic ice sheet in West Antarctica is flowing faster because of global warming, whether or not the ice streams that are releasing more water, well, more ice, which then contributes to sea level. You know, do you think that's just natural variability, or do you think there's a significant global warming component to that, or is it more ocean-driven or atmosphere-driven, or both? Do you want to comment?
Well, most people that's been working with the acceleration of the ice streams, which kind of accelerates sea level rise for us, they claim it's the ocean that's warming, and it melts more ice under the ice stream, so it lubricates the system, so it flows faster. But when we look at the bigger system, I'm sure most people would say the atmosphere moves equal amounts of energy just the other way as the ocean does. I think the ocean has a big role, but I would say when you hear about the measurements of ocean warming, I don't think it's sufficient to explain the increase of the ice streams. So I was wondering if you have to look inland on the ice sheets, because when it gets warmer, you also expect more snowfall, and then you have more mass to move out. And I think that's also an important component.
Okay.
And how about the sea level rise?
Sea level rise in itself certainly also accelerates the ice streams. I think so. I think it's known that during the glacial time, the most important kind of reactor for Antarctica to change its volume is sea level rise, because ice sheets in general has to stand on rocks, not float away on the ocean. So when the ocean goes down, then you have more rock to stand on, and the ice sheet can expand.
I can add a little bit to this with the ice shelf, because this is actually what we work on, is the ice dynamics. And I think you have to see the global climate change as an overall driving factor, because no matter what, in the long-term perspective, it is changing. It is retreating because of the overall climate change, but it doesn't do it in a linear, nice, easy fashion. The marine ice, which we call marine ice, the extension of the ice shelf, etc., they are really, in a way, very sensitive for dynamic changes. For example, the collapses you see, that's a mechanism that just releases from a lot of meltwater that gets down into crack and break up the ice. And you have what is called marine ice cliff instability. When you get to a certain level of a high ice cliff, retreating backwards inland, where it gets deeper, you come to a threshold, and then that just leapfrog back in. So you will see these changes in a very abrupt fashion. We have actually observed it in the paleo records as well. We have several new results, and very exciting. It just breaks up massively, very rapidly.
How fast?
Oh, this is a month. I mean, this goes very, very rapidly. You showed the satellite image of Larsen B. This happens instantly. And it does it like in a leapfrog fashion, but then it might find other stable positions, and it would probably sit there for a while. And that's dictated in terms of geology and other complex parts. But the overall driving is, my belief is climate and changes of ocean circulation pattern, where we get the warmer water coming into these areas, which we observe up in northwest Greenland, for example. We have warmer water coming in towards Petermann Glacier. It's one of these examples. So the overall and then the leapfrog pattern in between.
But I want to add just one more thing. That is, these very, very big events that we catch so beautifully on satellites now, have to remember we haven't been able to do that for a long time. So we don't have very good statistics on how often these things happen. So, I mean, there is also a kind of a, what you say, a component of big events in it, that we need to have good enough statistics to understand it. Because I guess Petermann and perhaps also Ice Stream B could have also released big pieces of ice back in time. We just don't know it.
They most certainly have.
Exactly.
Because this is what we found in Pine Island Bay. We had a massive collapse there around 12,000 years ago. So it's that then the ice system was further out. But we do see these things. It's ice dynamics.
So it's something we discuss a lot, is if it's, you know, how much you can ascribe to climate change and how much is natural behavior. Sorry to interrupt.
Any questions from the auditorium here to the panel?
Okay, thank you. My name is Cheryl Schustrom, and I'm a researcher here at Lund University, trained as a sustainability scientist. Thank you for presenting today. And I think it's really important. When I also started my career, well, sort of anyway, started becoming a scientist, the success story of the, I saw you have the light right in your eye, sorry about that. Can't really see me, good. The success story of really the coming together to solve the ozone hole problem it's really important that we have it in our backpacks. However, when we look at, and both of you have really touched upon this in your presentations already, and I'm wondering if we can talk a bit more about the new nature of the problem of climate change, where all of the wonderful P's, the 1, 2, 3 P's that Susan talked about, they've turned into I's instead of P's. They're now suddenly imperceptible, at least if you just watch Fox News in the US, for example. Or you can get away from the simplicity or sort of the clarity of this is really a problem of climate change. You can actually hide yourself from it. It's impersonal. As you said, the first people to get impacted are not you and me, but it's the ones who are growing, you know, the small-scale farmers, for example. If their crops die, then that's it. And also impractical. I mean, for you and me to change our lifestyles, we can do it, but it's not necessarily, I mean, our lives are kind of based around flying and eating this and cooling and heating and transporting ourselves in a particular way. So I just wonder if, so it's not really a direct question, but sort of we're in a new historical time than when we were when we learned about the ozone hole and sort of fixed it. How do we deal with these challenges that are both, it's both about knowing the science. The science itself is very complicated, but then there's also the part of the people, the humans who are, who have to also make the changes, but we're in a different historical time that these, making these changes.
Honestly, I don't think we are in a different, I mean, yes, we're always in a different historical time, kind of by definition, but honestly, I don't think that people of the 21st century are necessarily less capable of solving environmental problems than people of the 20th century were. I think that you can actually point right now to something which is moving at incredible speed to solve a major problem, and that's plastic. We've recognized that it is extremely practical not to use plastic the way we have been using it. And the speed at which so many communities and countries, entire countries, are taking action to stop the use of single-use plastics is, to me, incredibly uplifting. It is eminently practical. It is perhaps personal, because it's even in our water bottles. And it's certainly perceptible when you go to the beach, and it's horrible how much plastic there is out there, right? So when you get to the issue of global warming, I don't think it's impractical to think that we have to change our energy system. We have to do it anyway because we're going to run out of oil. So the sooner we do it, the better it is for everyone, actually. But quite beyond that, if you're a wise leader of people, or if you're a wise voter, you will think about the fact that there are other options. They're not terribly expensive. In fact, in some countries, solar energy is very competitive now with fossil. Even Saudi Arabia is heavily investing in solar at this moment because they know they're running out of oil and they know they have plenty of sun and will continue to have plenty of sun. So I think it's not hard to say that actually in this case, in the case of global warming, I think the practical will be the driver, because we will see more and more practical ways to do other things. We will see more and more co-benefits to our health in things like reducing air pollution. The Chinese have certainly recognized that they have a very serious air pollution problem, and one of the best things they can do is reduce their emissions of, for example, coal, stop burning coal. Will have huge health co-benefits along with the climate benefits. So I think the personal side does exist. It's a little more complicated. The science at the moment could be argued it's not as perceptible to most people, but I'm not sure that's necessary when the practical drivers and the personal drivers are becoming strong enough, actually, in the countries that do something about it. And of course, here in Sweden, you've shown a great model for how you can decarbonize while you grow your economy. It can be done. So obviously it's practical. You did it. I don't accept 3 eyes.
Any more questions?
Yeah. Well, I could just add that I think it's important to recognize that important is to really do something about the CO2 emissions and the greenhouse gas emissions, and don't think that there are any quick fixes. Don't think that you can solve it by working on these short-lived climate pollutants or any geoengineering or any things like that. We really have to focus on the CO2 emissions. And if there is the co-benefit of also reducing the air pollutants, that's great. But we have to focus on the CO2 emissions.
I couldn't agree more. Totally agree with you.
I was wondering, are there any estimations on or quantifications on the ozone warming effect compared to, for example, CO2?
You mean tropospheric ozone, smog?
Yes.
Yeah. There are. And from memory, it's, I think the best estimate of how much our air pollution ozone, totally separate from stratospheric ozone, it's about 1/3 of a watt, if I'm not mistaken, per square meter. And CO2 right now is what, about 2 watts per square meter? So it's
pretty much.
It's 10%, 15%, maybe.
Dr. Solomon, you said if there are wise leaders, but if there are not wise leaders, if we assume that 3 of the largest countries, China, India, and the United States, didn't have wise leaders, how big a delay could that be? What would happen?
Yeah, well, this is a problem. As I said, the individual can't impact this problem directly the way we could with the spray cans. I mean, it was a fantastic thing that consumer choices, don't know if I remembered to say this, but at the time when the spray cans were tossed aside, they were about 75% of the global emission of chlorofluorocarbons. So individual action, which was not difficult, could make up a huge fraction of the problem. Whereas in this case, individual action, as was pointed out by the young lady interested in sustainability, is much more difficult. You know, we fly, we have wonderful electricity, we have all these great conveniences, and it's just much harder. So we have to look to leadership of our major, particularly our major innovating nations to advance things that will make it cheaper. You know, I mean, if the technology advances, then the market will follow. And that's, I think, what we're seeing. You've seen tremendous decreases in the costs of renewable energy over the last 10 to 15 years. And a lot of that, to be fair, you know, China has driven that. They have invested. There has been some investment in other countries too. In our country, we have actually done some useful things. So I think that we have to demand more out of our political system. That's what it comes down to. It is a tough problem. No one's going to say it's an easy problem.
This may be a trivial problem and a silly question. Our king has recommended that we stop using bathtubs and convert to the shower. So my question is, how important is the household use of warm water?
Okay, I guess I'll take a quick crack at that one. Certainly, anything you can do to reduce your household consumption is a good thing to do, and he's correct that it does use a lot. It's actually also a big use of water. So the part of the carbon footprint of it is all the purification and processing of the water to get it to you. I mean, it's drinkable water and you're going to soak in it. You know, when you think about it, it's sort of wasteful in that sense. But it's also wasting carbon. So indeed, it is a significant thing you could do for the environment, is not to take baths. Showers probably get you cleaner anyway. But I think the other thing that has been well demonstrated is that the single best thing you can do to reduce your household carbon footprint is actually not to use a clothes dryer, but hang your clothes outside whenever the weather will permit that, which of course isn't the case everywhere all the time, but if you can do it, that's the single best thing to do. The second best thing you can do is get a very good, very efficient refrigerator, which I think in this country you've done a great job with, as I understand it. You know, in our country, we have these ridiculously enormous refrigerators that are only limited by the size of the front door of the house. So, you know, there are things that can be done, but those are the two biggest things. Dry your clothes outside and get a good refrigerator, which you probably already have. And baths are
I have a...
Okay. Torste?
No, I was thinking, when we're talking about water, I mean, the situation in Johannesburg, where they're going into a total lack of water, that they're not allowed to wash their dishes anymore. And it's really, I think it's in July that they expect that they will be totally out of water with something actually fantastic.
It's been delayed now, but okay. Because people have been conserving so much, they've fended it off a bit. But it's a serious problem because of what Professor Manabe alluded to, the drought increasing in parts of the world, and South Africa is one of them.
But it also shows that water is very valuable, and we are really using a lot of groundwater in many of our countries. The groundwater level is going down, and we are simply wasting a lot of water instead of collecting rainwater for many things. We're using very, very precious water for things like soaking your body. That I think this is something we'll see will change the next 20 years towards a more sustainable way of doing it. Yeah.
How long will the groundwater last in southwest US?
I don't know.
Not too long, I think.
Yeah.
Yeah.
Hello, thanks for an excellent discussion so far. My name is Paul Miller. I work with a strategic research area dealing with climate models here at Lund University. I'm fascinated with the link between the ozone problem the ozone hole problem and climate change. I'm just wondering about your opinions on the fact that possibly one silver lining to the ozone hole problem was that we now understand the climate system better. We understand the complexity of the Antarctic climate system much better now because of this. And also because one added benefit might have been the fact that we can now demonstrate to the world community that we can actually deal with a major environmental problem if we all work together. So both political benefits and maybe scientific benefits, even though originally, of course, we wouldn't have liked to have seen the ozone hole develop at all. Okay.
Well, I guess that one's for me again. Sorry about that. I certainly agree with you about the ozone hole being a remarkable success story. It's often held up as the signature environmental success story. It's useful to remember that there's some more, actually. It's not unique. We've not completely solved, but we have substantially managed acid rain, I believe for many of the same Ps as I talked about for ozone. Similarly, in the developed world, we've done a pretty good job of cleaning up air pollution in many of the major cities. Children can play outside today in Los Angeles. They couldn't do that in the 1960s. It's not perfect, but we've done a pretty good job there too. We've got lead out of paint and out of gasoline. Still have some issues in pipes. And that actually tells you something very important, which is that we do a much better job when the infrastructure investment isn't big. So, it doesn't cost really more than 50 cents to throw away your spray deodorant and buy a new one. At least back in the 70s it didn't. Now it's a bit more. But and similarly in all the cases I've mentioned. But the expense of getting the pipes out of the ground is the reason that we haven't done a better job of getting rid of lead pipes. Instead, we've had this terrible problem, which you might have heard about in Flint, Michigan, where they switched their water system and the children got lead poisoning in Flint, Michigan. Poor community, so the poor are always the most vulnerable, and it shouldn't have happened. And it tells you how important regulation actually is, because the reason that it happened was because the people who should have been carefully regulating how the water supply was going to be handled in view of the lead pipes weren't doing the right things. But, there are many examples of how successfully we have actually managed a whole series of environmental problems. And we should celebrate those and learn from those and use them to think about climate change, which is what I tried to do in a small way this morning. But when you go on to talk about the Antarctic climate system, yeah, I would say that it's fair to say that understanding why Antarctica is behaving so differently from the Arctic is obviously a matter of scientific fascination. And seeing the kind of behavior that we see, one of the really cool things to me is that the west side of the Antarctic Peninsula is warming more than the east side. And the only difference between them is this big mountain range in the middle. So the west side is getting that stronger wind flowing in that I showed you in the picture. We know that's happening. And the east side is somewhat sheltered. So the west side's getting the biggest effect of the change in winds caused by mainly the ozone hole. There's a small contribution from greenhouse gases too, to be fair to that. And that contribution will grow. So yeah, we've understood how important the winds are in dictating the whole climate of the southern hemisphere much better, because we had this big perturbation. We had an experiment, and we made measurements to understand what was going on during this man-made experiment. An exciting thing to do in the next 40 or 50 years. If I was a young scientist today, I'd be saying, well, an interesting thing is going to be, how is the region going to change as it shifts, as the ozone hole fully recovers? Can we measure all those things that we need to see to tell us how much of an effect is now happening? So, yeah.
Could I add that there is a difference between Western Antarctica and Eastern Antarctica as well? That is that by far most of the mass loss from Western Antarctica is the big ice streams. So there's some a few major ice streams that basically take all the mass out of Western Antarctica, while this is not the case for Eastern Antarctica. So it's different processes that lead to the mass loss in the east and the west, and I think that's also important.
Yeah, that also shows how much the ice is part of the climate system.
Yeah.
It's not just the atmosphere and the ocean.
It's two fundamentally different ice sheets.
Yeah.
So I have a question for Professor Manabe. If you would project the future of climate models, what would you think? Where will it go? Where can we gain the next steps in the next generation of climate models?
What I think is the model I presented here is continental ice sheet distribution is given. But one of the major issues we are facing is we have to determine, or we have to be able to anticipate what's going to happen in continental ice sheet. And because some crude climate model, which put that into the model, predict that ice sheet, Greenland ice sheet, may disappear in the matter of a few centuries. But of course, model is so crude, and these beautiful ice stream, which you can see from satellite monitoring, beautiful, but you know, if you try to model that ice sheet in the our model, or any model there, properly, it's very, very difficult problem because these ice stream is very narrow and keep coming down like this, and the bottom of the ice sheet, there's the ice melt gliding through this melting water. And how you can quantitatively model that seems to me it's overwhelmingly difficult. But it's very important because if you Greenland ice sheet, suppose come down into the water, ocean, and then sea level will rise about 6 meters. And if you look at the maps where you raise the sea level by 6 meters, my golly, many of big cities are underwater. And so that, but we can't deny the possibility that it may disappear. I always thought it maybe we can wait about a few centuries, several centuries. And in that case, then, when Columbus came to U.S. is how many centuries ago, the time scale. So we may have a long enough time moving city backward into inland and so forth. But on the other hand, if it's coming in 1 or 2 centuries, few centuries, then it's a huge problem, isn't it? And I think this is one of the most interesting challenge in the future development of climate model. And in my opinion, that seems to be the most important issue we face.
Birgitta?
Yes, I just wanted to add one thing, that one important addition to climate models that is actually ongoing now is to also include the biosphere and the dynamic response by the vegetation and the carbon cycle and so on. And this is a work that's going on partly here in Lund in the strategic research area MERGE that Paul represents, who talked here just recently. And I think that's an important addition that's going on at the moment.
So essentially what we see is that we are working now on very advanced ice sheet models, but they're not fully coupled into climate models. They're not integrated. So the future would be try to integrate it more and more. And it seems to me also that that's an enormous challenge to get fully integrated models.
Yeah. You know, we create these large-scale climate models, the grid size of, I have been using 500 kilometer or 300 kilometer grid, big boxes. Now they go into 50 kilometers. But to resolve ice stream,
much smaller.
Just imagine, you may need only few kilometer grid sizes, right? And I told you earlier when you asked a question that what you do, see, big scale problem are parameterized based upon law of physics, but subgrid scale process called parameterization. And so now people try to compete with nature in complexity, put more and more things in there. But the question is, Subgrid scale is no less complicated than above grid scale. So it's just like a fractal. You go smaller scale, then you get another universe, which is as complicated as the larger scale, right? And that's why parameterization is so damn difficult, right? So my philosophy throughout my career in climate modeling, if you want to make more complicated, competing with nature, is my understanding of that process warrant that complexity. And that's one of the reasons that like cloud process, if you once you get inside a cloud, droplet and ice crystal, and then they collide each other, and turbulence, convection, and they all mixed up together, right? And then if you try to parameterize that thing, just like ice sheet. So, or you look at a land surface, it's so darn complicated. All you have to do is just open the window, and then just model one trees requires several computers, right? And so this is one of the very interesting issues. That's why cloud parameterization is so difficult. So uncertainty in climate prediction hasn't reduced last several decades.
Dorte?
Ice sheet, modeling the big ice sheet is a very young research field.
Yeah.
It's actually started at least 25 years after atmosphere models.
Oh.
And it's still to a very, very high degree one-man projects, a PhD project, a postdoc project to do. And I think one of the things, a challenge we face now is that we need to look at it like we look at the atmosphere models, that you need to make a center for ice sheet modeling where you have a bigger unit that really can work with all the difficulties in a model before we can solve it. Because I can, from Emian, 130,000 years ago, we actually know it was 2-3 degrees warmer than now. But we also think that the sea level was 6 to 9 meters higher at this time. So I mean, we are warming now, and ice sheets respond slowly. But we can really expect a very, very big sea level rise based on the warming we are doing. And just to end my story, and to kind of supplement your telling, then from the ice core community, we're actually drilling an ice core through an ice stream in northeast Greenland, exactly because we recognize that this is the place we know nothing. So if we need to understand the processes so we can put them into the models, we need to understand what's going on, how they are sliding, how they are shearing, and what's going on. So this is what we are trying to do.
I think that's a very good end of this discussion. So, thank you very much. And now it's lunch. So please help yourself. I think it will arrive or have arrived.
No, I think we have a few minutes.
Okay. Yeah. Well, then we can, another question, if, please. Something you thought about? Yeah?
It's so complex for the common man, and I'm a common man. I'm attempting to integrate all of the different fields of research. And it was just very interesting with both the ozone and the global warming. But the idea of convergence, scientific convergence, just discuss the importance or what will be evolving as being the solution to the greatest problem that's facing mankind.
You mean to converge different systems of Earth?
It's too difficult a question. I'm going to pass it to Martin.
No, I think this is what you see in a sense, that we are the first slide I had there, geoscience, is about learning the entire, or understanding the entire Earth system, and we certainly cannot do that by field by field by field. We must work together, and this is really what you see. This is a new trend. We are always working on any expedition I go, for example. We will have everything from modelers to people doing observations, from oceanographers to geologists, and even biologists, I say today. Everybody are trying to solve the puzzles. So I think you see a lot of conversion in the science, and it's not happening over one night, but it's going. It's happening more and more. At the same time, you need to also have the people that are focusing on a very small problem to resolve that little piece.
Evidentiary authenticity.
Yeah. Absolutely, but I think even there we have a great number of good mathematicians working along and chemists working along, just getting attractive to the problem of solving outstanding questions. So I think that's maybe one of the biggest changes, that we see more and more interdisciplinarity for the good.
One last. How was it 40 years ago that scientific reasoning was an accepted norm, and now it isn't? In terms of the ozone and in terms of the erosion of respect for the scientific community?
Well, that's a fascinating topic. You know, there's a book called, I think it's called, Is the Internet Making Us Stupid? And, you know, it's a double-edged sword having all this information available in a new way. We haven't, I think, fully learned how to handle the rapidity with which information can flow around the world now. You know, in the old days, the speed of dissemination was helpful in a sense. You know, you couldn't get wrong. The problem we have now is that bad information spreads faster than good information. Good information has to be peer reviewed. Bad information, you just put it out there on Twitter or who knows, you know, Facebook, and pretty soon everybody believes it. It's a serious, serious problem. And I think that as society figures out how to handle that, and I believe we will, again, I'm an optimist, even though I don't have a solution, it's going to help us a lot. I mean, the examples from fake news, people are beginning to recognize, I think maybe this is the most hopeful thing I could say, people are beginning to recognize how dangerous fake news can be and that it actually exists. And a great example of that was during Hurricane Harvey. There was a fake news report of sharks swimming through the streets of Houston, right? And it actually spread like wildfire, and people believed it. And it actually delayed some of the people who needed to get help getting help. And it's just unconscionable that we let stuff like that, you know, become our method of getting information now. So we have to get to terms with making the internet the wonderful information service entity that it certainly has been and can continue to be. But it's not by just letting it be the wild, wild west, and that's what we're doing right now.
That was a great end, I think, Susan.
Thank you.
Some information here.
Yes, hello again. Before you leave, I would just like to take the opportunity to, on behalf of the museum, recommend our temporary exhibition upstairs. It's called The Weather War by Swedish artist duo Bigert and Bergström, and it deals with the topics of climate change and geoengineering, so perhaps something you might find interesting. And of course, you can't bring your lunch upstairs, but you're more than welcome to bring yourselves. Thank you.